Hello, calculus fans. We're going to talk about line integrals now. This is a similar integral to the one that we saw in one variable calculus. Instead of integrating over an interval a to b, we'll integrate over a curve. These integrals are called line integrals, although really curve integrals would be a better description. Line integrals were invented in the early 1800s. They're used to solve problems involving fluid flow, forces, and especially electricity and magnetism. What we'll do is we'll start with a plane curve given by these parametric equations. We'll say x equals x of t, y equals y of t, and the t values go between a and b. Equivalently, we could say that we have a vector equation r equals x of t, y of t, and we're going to assume that c is a smooth curve. That means the component functions have continuous first derivatives. So what we'll do is we'll divide the parameter interval a to b into n subintervals of equal width. And then we'll let x sub I equals x of t sub I and y of sub I equals y of t sub I. Then we have corresponding points p sub I, which divide the curve into sub-arcs with lengths delta S1, delta ST, and so on up to delta Sn. Let's take a look at a picture. Here you can see we have a curve that's divided up into sub-arcs. We display the parameter interval at the bottom, the interval from a to b. That's been divided up into subintervals, and then the partition points correspond to various points on the curve. We'll then choose points p sub I star somewhere in the ith subarc. It's like a sample point. This corresponds to a point t sub I star that's somewhere in the interval from t sub I minus 1 to t sub I. So if we have any function of two variables whose domain includes the curve c, we'll evaluate that function f at the point x sub I star, y sub I star, then we'll multiply by the length delta si of the subarc and add all this up using this sum. That's similar to a Riemann sum. In fact, it is its own particular type of Riemann sum. Last thing we do is we take a limit of these sums, and that leads us to the following definition. This definition is going to be analogous to the definition of a single integral. So we say that if we have a function that's defined on a smooth curve C, given by parametric equations x equals x of t, y equals y of t, where the t values go between a and b, then we define the line integral of f along C to be the limit as n goes to infinity of the Riemann sum that we talked about before. And the notation we'll use is an integral with a c below the integral sign of f of xy ds. This is all, of course, provided that the limit exists. Now remember, in one variable calculus, we came up with this formula for the length of a curve. So we have the integral from a to b of the square root of dx by dt squared plus dy by dt squared, integrated with respect to t. So we can make a similar argument to show that if we have a continuous function f, then the limit that's in the definition of a line integral will always exist, and we can use the following formula to evaluate line integrals. So the line integral of f along c with respect to s is equal to the integral from a to b of f of x of t, y of t, times the square root of dx by dt squared plus dy by dt squared. And this is all integrated with respect to t. And what you're looking at here is an ordinary integral of the type that you saw in one variable calculus. It turns out that the value of the line integral will not depend on the particular parameterization of the curve. This is as long as we only traverse the curve once as t goes from a to b. Now, if S of t is the length of the curve between R of A and R of t, then we can say that ds by dt is equal to the square root of dx by dt squared plus dy by dt squared. So here's how we can remember the line integral formula. We can express everything in terms of the parameter t. So ds is equal to the square root of dx by dt squared plus dy by dt squared, dt. Remember, this is not a real thing. This is just a mnemonic device. Now there's a special case where C is the line segment that joins the point A0 and B0, and we use x as the parameter. Then we can write the parametric equations of C like this. X is just x, y is 0, and x goes between A and B. Now our line integral formula looks like this. It's the integral over C of f of xy ds. That'll equal the integral from a to b of f of x0 dx. So that means the line integral just reduces to an ordinary single integral. Now the last thing we want to do is give an interpretation of line integrals. Now just like with single integrals, we can interpret the line integral of a positive function as an area. If we have a function f, which is non-negative, then the line integral along C of f of xy ds will represent the area of one side of the curtain in the following picture. The base of the curtain is the curve C, and the height of the curtain above the point x comma y is f of xy. All right, let's look at a picture of this curtain. So the line integral will represent the area of this curtain. Okay, that's all for now.